Good morning, ladies and gentlemen. It's a pleasure to be here with you today. First, I would like to introduce myself. I am Claudia Gadizza from Universitas Brawijaya. My presentation this morning will concern primarily about short review nanocellulose for smart biodegradable packaging in food industry. Now we are going to the first slide. To begin with, I will speaking about the potential of the nanocellulose. Cellulose is the most abundant and renewable component of the plant cell wall and source of polymer on Earth. Cellulose global production of nearly 7.5 million tons. In recent years, nanocellulose has been widely studied due to the public awareness of naturally sourced products. Nanocellulose has very high surface area, crystallinity, and has a tunable surface chemistry that can be adjusted. However, the use of bio-based material for good packaging is still limited due to their usually poor physical property. This feature gives the nanocellulose material great potential to continuously enhance the property of oxygen and water vapor barrier when used as layer filler in composite and as thin film stencil. Merging referencing structure such as nanocellulose into this material can be improved this property. Nanocellulose definition and classification. To obtain the nanocellulose crystal or fiber from cellulose chain, we can adopt chemical and mechanical technique or by using microorganisms. Acid hydrolysis and enzymatic hydrolysis are chemical techniques which often used to obtain cellulose nanocrystal. While the mechanical technique, it can use high pressure method, high speed defibrillation of cellulose chain to occur and provide cellulose fiber into the nanodimensional ring. Bacterial nanocellulose synthesized from sugar source from glucose by a family of bacteria is involved through the bottom-up approach. And then we are going to the comparison of the nanocellulose family. In general, nanocellulose is classified into three. The first is nanofibril cellulose. We also M.Si. And then the second is nanocrystal cellulose. And then the last is bacterial nanocellulose. M.Si is generally generated through the defibrillation process mechanically, such as homogenization, while M.Si extracted after going through several types of process, for example, alkaline treatment, homogenization, and then acid hydrolyzation. While the bacterial nanocellulose produced from bacterial and also known as bottom-up method. The formation and average size you can see on this table. And then we are going to the preparation method of nanocellulose biocomposite. Numerous methods have been used to prepare nanocellulose composite, such as solvent casting, supercritical solvent impregnation, and then physical mixing, in situ polymerization, extrusion, and layer by layer formation. To develop active and intelligent packaging, gas biocompounds such as antioxidant, antimicrobial, bioindicator, pH indicator or immunoassay, anti-UV, and absorber, gas absorber or emitter. We have two different methods. The first is impregnation ex situ, and then the second is bottom-up build method. Nanocellulose can also act as a carrier of active agent and have a role in the active or intelligent packaging. The application of the nanocellulose biocomposite as smart packaging. To conclude the application the nanocellulose in smart packaging, the list of application of nanocellulose to improve the novel functional properties is shown in this slide. This is the bioactive compound such as the condensed tannin, nisin, clove oil, mango leaf extract, pine needle, rosemary essential oil, and then the sum of nanoparticle, activated carbon, and then the last is bioindicator like anthocyanin from the black carrot extract, and then the last is the betanin. We can also use the matrix polymer from nanocellulose such as cellulose nanofibril, oxidized nanocellulose biopolymer, cellulose nanocrystal, nanocellulose by tempo-mediated oxidation, bacterial nanocellulose, and then the last is hybrid nanocomposite reinforced with the bacterial nanocellulose nanocrystal. We can see the application of the smart packaging from biocomposite nanocellulose. The first for dry food like rice or pasta, preserved fruit, vegetable and meat, ready to eat ham, pork, chicken, pasteurized milk, rainbow trout and common carp, and fish fillet. And then the objective, the application of smart packaging is, the first is to increase shelf life, to delay oxidation, to inhibit the growth of foodborne pathogen, have a role in UV blocking, improve the mechanical property and water vapor barrier capacity, and then the last is for monitoring food quality and food safety. We will talk about the future perspective of nanocellulose-based smart packaging. Nanocellulose has the potential to be developed into the smart packaging material for food product. Based on its physical and mechanical characteristics, nanocellulose has a great opportunity to be used as a polymer matrix and has been able to meet the requirement of food packaging. The addition of active ingredient can be through the method of making biocomposite, nanohybrid, the impregnation, and coating. To improve the physical, mechanical, moisture and gas barrier, antimicrobial, antioxidant, and anti-UV property of nanocellulose, it can combine with other material through several methods. The result of numerous research study has established the potential of effectively employing active and intelligent packaging system based on nanocomposite matrix for improve and monitor quality of various food products. Further improvement can be focused on enhancing safety, and research can be carried out to ensure the prevention of toxicity in the film, which may be caused due to degradation when exposed to the natural environment, and thus produce stable packaging. To conclude this review, the first conclusion is the effective potential of nanocellulose biocomposite as the matrix for develop active and intelligent in improving and monitoring quality of food product has been demonstrated by several recent research. The selection of nanocellulose material preparation method and the selection of active ingredient that play a role in active and intelligent function in packaging greatly determine the success of the nanocellulose application in food packaging. The main criticism appear to of the difference between the result obtained in the model test and real food storage condition. Though improved the physical, mechanical, the complexity of food system is evident. Different quantity of the packaged food ingredient, fat ratio, and distribution and non-fat part fluctuation and variability of the physical and chemical parameters such as water, pH, etc. I think that's all. Thank you for your attention.